homework 3 is due, what did we say, by Wednesday? Homework 4 should get posted. Tomorrow. I've been bringing the same bad pen to me. Okay. Yeah. I know. We just had a midterm, and now we're thinking about this. But are there any questions on homework 3 we should try to address? Okay.
No.
Okay. And so, well, let's start thinking about this. And by the way, I hope that midterm went well. I'll be grading it over the weekend, and if I'm really hoping to have it for you for Monday. Yes. Okay. Well, so we've introduced random variables, and so far I'll say, we've introduced, wait, this pen is dying too, discrete random variables, okay. Probability mass functions, what else? Cumulative probability functions, expected values, particularly the mean and the variance. Okay. And we also mentioned functions of random variables. Okay. And also some functions of random variables. And I list that all out there in 2.1 through 2.4, because now that we've seen kind of the lay of the land, what we want to do is start talking about a couple specific special cases. Of course, one could construct an infinite number of discrete random variables. There are some, a handful that are particularly useful and particularly germane to us. Okay? And so, some specific discrete random variables. Okay, and the first one. And by the way, as another brief kind of introduction, suppose that for a random variable, call it x, with a probability mass function px of x. Okay, suppose that if this probability mass function, right, depends on some kind of a quantity, that can take a variety of values. This is a kind of a terrible sentence, though. It's fairly common. Such a quantity is called a parameter. Okay, and the collection of all probability distributions for all the different values that parameter can take on is called a family of probability distributions. Okay? And so, a collection of probability distributions for all the values that parameter can take on and be take on is called a family of probability distributions. And so when I say we're going to talk about some special cases, what I mean specifically is we're going to talk about a couple families of distributions, right? Right? For instance, if you're the experiment is we toss a coin 10 times and we let X be the number of times it lands on heads. Well, the probability of a head is 0.5, right? Right? And suppose we said we're going to roll a dice 10 times and let X be equal to the number of times it lands on 6, right? Okay. Well, in that case, P is the probability of a 6 is 1/6, right? Except for those experiments and those models are absolutely identical, with the exception that one uses a half, the other uses a 6. That's what I mean by this family of distributions. They would fall under the same umbrella, right? Right. The only thing that's changing is the parameter, that 1/2 to a 1/6, right? Right. So that's kind of what we're getting at right there. And so, as you've seen we do in this course, we tend to start with the very basic and try to build up from there. And one of the very basics is a Bernoulli random variable. Okay. Bernoulli random variable. Okay. And what a Bernoulli is one single trial that can result in a success or a failure. Okay? Okay? So we have one single trial, right, that can result in either a success or a failure. Okay? And a success is some event A occurs. A failure is that event A does not occur. Okay? Okay? Where the probability of a success is going to be denoted lowercase p. Okay? Okay? And then we talk about our random variable. For random variable x, we assign a 0 for a failure and a 1 for a success. Okay? Okay? Right? And so by the way, the probability of a success is going to be defined as going to be lowercase p. Okay? So then the probability of a failure is going to be 1 minus p on that individual trial. Since we run into this paradigm a lot where we have successive experiments that result in either a success or a failure, this failure probability comes up quite often gets shorthanded with the letter Q. okay, okay. Often assigned the letter sheet. Okay, okay. So the probability distribution, is as simple as it gets. We have one single trial. Our random variable x can either be a 0 or it can be a 1, no other choice, right? The probability that it's a 1 is p, so there's our px of x, and the probability of a 0 is a 1 minus p. Okay? Okay? And so, you know, for instance, and by the way, such, change color here, such a random variable we'll denote as x has the distribution. I'll use a tilde like that to mean has the following distribution, that it's a Bernoulli, and a Bernoulli random variable has one parameter. That parameter is p. Okay? Okay? P. Right? For instance, right? As I said, flip a coin one time. A success is it lands on heads. Right? So then we could say x is Bernoulli, and p is 1/2. Right? Right? As opposed to roll a dice, define a success as it lands on 6, right? X can still be a Bernoulli, assigning either a success or a failure to that single experiment, and p would be 1/6, right? Right?
Oh yeah.
You see what I mean? And so this is generally describing an infinite number of things for any value that p could take on, right? And so
It's like if you had a dice race and we do 2 times, it's gonna be 1/36.
well, I don't know about, it wouldn't be a Bernoulli.
Oh.
Because a Bernoulli is one single trial. Right?
Oh, okay.
Right?
Okay.
Now, so, but let's continue with that thought, right? Because this is literally where it's gonna go, right? Suppose the experiment is I'm gonna roll a dice twice, right? Right? Well, see, the thing is, and then count the number of heads. Well, each of those trials is a Bernoulli. And so we're adding 2 random variables together, a Bernoulli for the first trial plus a Bernoulli for the second trial, right?
Okay,
Right?
okay.
That's where this starts to grow, okay? And so if this random variable is Bernoulli, I'll spell it all out with parameter p, okay? That's its probability distribution. Then the mean of x is, of course, the sum of the x's times their weight, right? Which is simply 0 times 1 minus p plus 1 times p, or p. Right? And so think about that in that context, right? If you're flipping a coin that one time and a success is that lands on heads, you notice that the expected value of x is going to be 1/2, right? Right? And so think about how that does or doesn't make sense in your world, right? Right? You know, if 50% of the time it's going to be 0, 50% of the time it's going to be 1, that average, that center of mass of that distribution is going to be right at 1/2, right? Right? Okay? And And then, let me see, the expected value of x squared is, again, that's 0 squared times 1 minus p plus 1 squared times p, and that is just p, right? So why did I care? Because I wanted to get to the variance. The variance is the expected value of x squared minus the mean of x squared. Right? That shortcut form we developed last class or the class before that, and that looks like p minus p squared, okay? Affectionately written as p times 1 minus p, or p times q. Okay, that's how that variance often gets written. Okay. Okay. So by the way, okay, let x be a Bernoulli. P equals 0.25. Right? That means, by the way, it can either be a 0 or a 1. What's the probability that it's a 1? 0.25, which means the probability that it's a 0 is a 7.5, right? Which means if you look at this distribution, there's a 0 and there's a 1, right? That it's got a height of 0.75 there, a height of 0.25 there.
Okay.
See what I'm saying, right? And what's the expected value of this? The expected value of it is 0.25, or indeed the center of mass would be right about there. Does that make sense? Does that picture kind of help with that?
Yeah.
Right? And so the mean of x is p is 0.25, and so right about there is where that mean would be. Okay? Good. And by the way, as we're working through these random variables, there'll be a little bit of a format, We'll introduce the random variable and when and how it applies. We'll talk about how to compute probabilities. We should also convince ourselves at the end of the day that we have a valid probability, okay? Namely, these are all non-negative and they add up to 1. I think that's pretty self-evident with that right there. But then also the probability is one half of the question. The other half of the question is what does the distribution look like, right? So we'd be talking about a mean, we'd be talking about a variance, maybe a standard deviation, kind of a sense of what it looks like that. Okay? How's that feel? Does it feel okay? Okay. So let's go to the first building block here, okay? And that's going to be the binomial, okay? And we've actually talked about the binomial an awful lot, okay? And so the next up is the binomial random variable. The binomial random variable, okay? And to start with, we have to define what's called a binomial experiment. A binomial experiment, right, consists of n trials. That n should ideally be predetermined. Okay. Yeah, that end should be predetermined. I once worked, I once worked in an engineering department, and we had some very, very smart engineers, and we were designing things. We were designing components for liquid chromatography systems, regardless, okay? One of the engineers was very bright, and they had designed a component, okay? and we tested it, and so we went through rigorous testing of it, and it wasn't passing, you know, which kind of like was a blow to his ego, is what was really happening there, you know, and he was like, can't we keep trying it? You know, eventually it's gonna work, right? But no, you can't. N's predetermined. You can't let N become a variable in this model, okay? So N is the number of trials, okay? The trials are independent and identical.
What is the meaning of trial?
What's that?
The trial, what does mean trial?
It means many things. It means many things. In other words, like if you're testing a component, you may want to test it 20 times.
Okay.
Each time you test it would be a trial.
Okay, like
Right,
a
right.
20 try.
That would be an N equals 20, right?
Okay.
Right? And so, but similarly, if you were taking a random sample of people, you know, each person you select could be considered a trial as well.
Okay.
Right? That's what I mean by it might take on a number of, but it's when you have these repeated experiments and the experiments have to be identical to each other. You know, you can't change the variables and things like that. And inherent in this model, the trials have to be independent. Okay? And it's called the binomial because each trial results and can result in either a success or a failure. There's no other possibility, okay? Right? There would be other models, but those would be things like multinomial experiments, okay? And so we're visioning this where I have this binary tree with n stages, okay? And almost always people write this, it feels a little redundant to me, but if each trial can result in a success or a failure and the trials are independent and they're identical, the probability of a success has to be a constant trial to trial to trial to trial, right? Probability of a success is constant for all trials. And we'll denote the probability of a success as a P, okay? In similar fashion, we'll define the probability of a failure
1 minus b.
as 1 minus P, and if we want to shorthand that, we can call it a Q. Okay. Great. What else? Oh, I haven't talked about the random variable. Okay. Random variable X, random variable X counts successes. Okay, right. And so, by the way, and we've been using this model actually in examples for several weeks now, right? For instance, the same thing, flip a coin 20 times, right? Let X be the number of times it lands on 6. That's a binomial experiment, okay? And so for this particular model, okay, and again, we've already kind of beaten this out of the woodwork, okay. And so first off, before I get there, a binomial random variable has 2 parameters, okay. Those 2 parameters are n, the number of trials you have, and P, the probability of a success on each trial, Okay? Okay? Binomial variable has two parameters, namely n and p. Okay? Okay? And so, you'll see me, right? If x has the distribution that it's binomial with parameters n and p, okay, then don't forget what values can x take on? If x is counting successes, what are viable numbers that x could be?
And P multiplication.
Does x have to be an integer?
Yes.
Yes. Can x be negative? Can x be 0? Yes. Can x be n plus 1?
Yeah.
How many trials you got?
And
How can you have 21 successes
Okay,
out of 20
no,
trials?
no.
Right? So the range of this random variable x is in fact finite, 0, 1, 2, 3, up to n. Okay? And so the probability mass function, is px of x, and maybe I'll write it like this. Okay? And remember, here's our whole model here, where if I have n trials, the trials are independent, and I want the probability of x successes, then don't forget there are going to be, then for every outcome, there are going to be x successes in it, and there'll be n minus x failures, right? And there might be a whole bunch of branches on that visual tree that would yield x successes, right? It's bringing us back to combinations and probabilities along the outcomes, right? And so the probability is n choose x, p to the x, q to the n minus x, and that's a little x, and that's for x equals 0, 1, 2, out to n, right? And 0 otherwise.
Why you have a 0 on both?
What's that?
Why you have 0 on both? Oh no.
Right? Zero
Oh, yeah,
is
yeah,
a
that.
possible input, right? It would be that event, that scenario where you ran your experiment n times and every one of them was a failure.
Okay.
Right. Okay, good. And so, interesting. And so, actually, is that a valid probability distribution? We might not do this with all of them, but I think we can with this, right?
Success.
Is this probability mass function a valid probability mass function? I'll just say probability function. Right? And so without any more ado, the two conditions are, one, that the probability is non-negative for all x, okay? And two, that the sum across all x in x of those probabilities must add up to 1. Right. Okay. Do we agree that condition 1 is met? That they're looking at that probability mass function. Could that ever yield a negative number? No. Don't forget, P is a number between 0 and 1, and Q is 1 minus P. So everything in there is positive or 0, you know, right? So that's certainly true. Do we have this one here? And the truth is, we actually have it almost for free, right? Right? Remember that day I was up on my soapbox talking about the virtues of combinations, right? Remember I mentioned the binomial theorem, right? Right? And so recall the binomial theorem. I don't know if it's fair to say recall it if you heard it for the first time here once in passing a couple weeks ago, but x plus y raised to the n is the sum. K goes from 0 to n, okay, and choose k, x to the k, y to the n minus k, okay? Okay, right, just in general, okay? So let's see this item number 2, okay? So the sum of the probabilities, right, across all x in x is the sum as x goes from what to x goes to what? What are the bounds on this summation? 0 to
n.
0 to n? 0 to n, right? Because remember that conversation we just had about what are viable values for x, right? So x is going from 0 to n of n choose x, okay? P to the x, q to the n minus x, and do you see that we've matched this form precisely?
Yeah.
Right? And that by the binomial theorem, that's gonna be p plus q raised to the n. Right? Well, you know, without any more deliberation, what is p times q? I mean, what is p plus q?
That's P
Probability.
plus 1 minus P.
Yeah,
So it's just,
it's
It's
just
just-
1, isn't it? Right? If on a given trial, the probability of a success is p and the probability of a failure is
1 minus p.
q, and doesn't that exhaust the possibilities? Isn't that just 1, right?
1. Yeah.
Right? And so that's 1 to the n, famously known as 1. So yes, we have a valid probability distribution. Okay? Good. And so, what else can we say? We'll get there in a second. Okay? Right. Suppose an experiment consists of we should use real numbers, but it doesn't matter. 10 independent identical trials. Okay, and success or failure for both. Failure for each, and the probability of a success is make up a number 0.3. Okay. So if we let x be the number of successes, right? This x is a binomial with 10 trials and each having a probability of success of 0.3. Right? Okay? And so find, so so, A, I'll put
Supposed
an
to.
A here. Find the probability that X is equal to 4. Right? What do I even mean when I say what's the probability X is equal to 4?
4 success.
Yeah, that 4 of the 10 trials resulted in a success, the other 6 resulted in a failure, right? And so, by the way, without any more ado, you guys have done this numerous times, but the probability X is 4 is the probability mass function evaluated at 4. It would simply be 10 choose 4, 0.3 to the 4 times 0.7 to the 6. Does that sound right? And does this ring bells of what we've been what we were talking about when we were in our independence conversation, right? Every single outcome is a string of 10 long, and there have to be 4 successes and 6 failures in some order, so each of those outcomes has this probability to it. How many outcomes have 4 successes in it? Well, that's the 10 choose 4. Okay. Now, I've told us on a couple different times that I encourage us in this course to use our calculator to our fullest ability, right? It really didn't hold any water until today, okay? And so,
I'm wondering, and instead of using that, we cannot use a p plus q to the power of the 10.
no, this is the probability mass, whoops, where is it? I've hidden it on us, right? That's the probability mass function.
Oh, okay. I might
Right.
confused. Yeah.
This was simply a demonstration that if I add up all those probabilities across all the viable values of X, that it actually really did add up to 1 and gave me a legitimate probability.
Okay.
Yes. And so, now I also want to, and I've got a TI-84, I don't know what you've got, but I do know that whatever you've got is a Google search away, but on my calculator, if I go to second, you see, let me zoom in a little bit. Fear of yelling at you, but there's the question we're looking at, there's that. On my calculator, under second distributions, the variable button right there, second distribution, you'll see a whole list of distributions, and this list keeps going. By the way, just for us, PDF stands for probability density function or probability mass function. CDF stands for cumulative probability function. Okay? And so, without any more ado, if I scan down here past the normals, by the way, normal distributions are those famous bell-shaped curves. They're continuous. We'll talk about them next in a week or so, a couple days anyways. But if I keep running down here, check out. There's a binomial PDF, there's a binomial CDF. Okay? For this particular problem, since we're asking for the probability associated with one single X value, probably the PDF button is a good one to use. Okay? And so that's equal to the binomial PDF. Okay, that's going right to my density function. And all of your things all your calculators might be a little different. The sequence of inputs are the parameters and then the X values, specifically N, P, and X. Okay? N, P, X. We used to have to do it like that. Nowadays, most of them give you a nice thing like that. What is the number of trials? It's 10. What is the probability of a success? That's a 0.3. What's the x value we're interested in? That's a 4. Okay?
So which tab is this on?
It's on mine, it's under second distributions. Okay? Right? Okay, okay. And 0.3 and 4. And even if yours doesn't have a nice menu like this, once you see what's it doing, you can see how it's doing it. There's the binomial PDF, that's n, that's p, and that's x. Okay? Okay? 0.2001 is about the answer. Right? See, that just saved you 5 minutes of computation time on the final exam. Okay, stick with me. Okay, that's CDF. Okay. For a binomial random variable, the CDF, the cumulative probability function, okay, capital F of x is, and this is just the definition, the probability that random variable is less than or equal to x, right, which is px of 0 plus px of 1 plus until you get out to and you include px of x, right? So if I ask you something like for what's the probability x is less than 7, right? Well, you can either compute using the PDF 0, 1, 2, 3, 4, 5, 6, and 6 and add them all up, or you could simply use the CDF, right?
So the CDF is for the cumulative?
Is the cumulative, yes. And I will go so far as to say that get used to those CDFs. The CDFs are really the money. Okay? And so for instance, find the probability that x is less than 7, is that what I said?
Yeah.
Right. Well, by the way, is that the cumulative? Should I evaluate the cumulative at 7?
No.
What should I evaluate it at?
6.
6. Right? And so that is the probability that x is less than or equal to 6. By the way, do we believe that sentence right there?
Yeah.
See, if x was time, then that would be a false statement, right? But x is something that we're counting. So since x is integer based to start with, that's a legitimate thing to say, right? And so that is the cumulative evaluated at 6. And for that, you can use the binomial CDF, okay? And simply, again, commands are NP and your desired x value. This will be 10.3 and 6, right? Whatever that turns out to be. Go back to second distribution and the binomial CDF, right? We've got, again, 10 trials. P is 0.3, and we're trying to figure out at 6, okay? And that's like a 0.989 or so.
Do you have this do you know how to do NT Inspire?
It's even easier.
Is it even easier on the Inspire?
Go to probabilities, and then it's the same after that.
Okay.
Yeah. See, actually, to be quite honest with you, I bring the 84, and don't take this the wrong way, but I bring the 84 kind of under the assumption that none of you have an 84, so I'm not showing favoritism to any one calculator. So I'm saying, you know, when in doubt, Google it. It's on your calculator, just go find it. You know
Okay.
what I mean? Yeah, and tell me on that Inspire, when you use that CDF command, does it actually give you a lower bound and an upper bound option? Oh, that is just too fancy. Okay, yeah. By the way, they don't all do that, okay? And, you know, see? Right? And so let me write on here on some calculators. Calculators. And we can say specifically the Inspire apparently. Okay? You can enter a lower bound, and an upper bound, with this CDF command. Okay. Right. And so, indulge me for just a minute though, because that might not be the case on everybody's, you know. So for instance, find the probability that let me see.
Can you zoom out a bit?
Oh, I'm sorry, yeah. There you go, is that better? Give it a second, it focuses.
Probability.
2 is less than x is less than 6. Okay. Right. And so granted, if your calculator allows you to enter a lower bound and an upper bound, you could do that. By the way, the lower bound, if you could enter a lower bound and an upper bound, what would the lower bound be?
2,
Would it be 2?
3, oh 1. Oh, no.
3. The upper bound would be 5, right? And so if your calculator doesn't have that lower bound, upper bound option, what else can we do? Well, that's the probability, let's see if I can just write it down here, is the probability that x is less than or equal to 5, right? But that would include 0, 1, 2, 3, 4, and so forth up to 5. Wouldn't we like to just remove from that x is 0, 1, or 2? Right?
Yeah.
Right? Minus the probability that x is less than or equal to 2. Right? And so that's a cumulative of 5 minus a cumulative of 2. Okay? Does that make sense for that?
Yeah.
Right? And by the way, what else could you do? You could use the PDF button, right? And evaluate it at 3, evaluate it at 4, evaluate it at 5, and add them up. You know? You see how that's working for us? Is that working okay?
I don't think I have the binomial CDF or PDF in my calculator.
Let me look at it during the break. Oh, it's almost break time. What happened to the time? We're supposed to get through 3 of these today. Okay, well, let me see. Oh, and so before we end the game, right? Let's continue. So if x is binomial n times p. Okay, okay. What is its mean? What is its variance, right? What is its standard deviation? Okay, and by the way, at least for the mean, and this doesn't happen in probability all that often, but the mean is what we would all think it is. You know, if you roll a dice. If you roll a dice 100 times, what would you think the expected number of times it would land on 6 would be?
100.
A 6, right? Right? You go 100 times a 6, right? Right? And that isn't exactly what happens. The mean is n times p. And the variance of a binomial is n times p times q. Okay? Okay? Right? And by the way, at least for the mean, I can make an argument. Okay? And so to argue the mean of x, right? Consider each trial, individual trial, right? Right? We have n trials total, right? So we could for each of those trials view it as a Bernoulli, right? Right? And for each trial, we could code the Bernoulli a 0 if it's a failure and a 1 if it's a success, right? Right? For each trial, let each trial be a Bernoulli, right? Where x sub I, right, can either be a 0 or a 1 with a probability 1 minus p or p, right? Right? And we've seen that the expected value of xi of each one of those Bernoullis is simply going to be p. Okay? Okay? Right?
The mean is p.
What's that?
The mean is p.
The mean is p of a Bernoulli,
Okay.
right?
Oh, okay.
Now, the money here is if we create all these Bernoullis that are 0s for failures and 1 for successes, and I have my original random variable x which counts the successes, how is my original x related to all these Bernoullis? Wouldn't the total number of successes be the sum of those n Bernoullis? Because the Bernoullis are 0s for failures, 1 for success. Right? Right? So we observe here that my original random variable x is x1 plus x2 plus out to xn, where these are the Bernoullis, and this is the binomial. Right? And so, and since the trials are identical to each other, the expected value of x1 is p, the expected value of x2 is p, so forth and so on. Now we see that the expected value of x is the expected value of x1 plus x2 plus out to xn. Right?
Okay.
Right? But we reached a really important milestone in one of the last, not in the midterm. I don't know if we reached any milestones there, but the class before that we did, you know. And in fact, we discovered in the class before the midterm that the expected value had linear properties. It distributes through sums and it distributes through constant multipliers, right? Right? And so this is the expected value of x1 plus the expected value of x2 plus all the way out the expected value of xn. The expected value of each of those Bernoullis is p, and that's where the n times p comes from. Okay? Which is n times p. Okay? Okay? Good, good, good. So, okay, it's about time for us to take a break. Are we feeling comfortable with the binomial and maybe some of those features on our calculator?
Yeah.
Yeah? Yeah? What you got there? In 89, oh, it's there. Do a little Google. There are some stats features in there. There's an app for it, and you might even have to download that. I'm not sure.
It's a titanium.
Yeah, no, it's absolutely, the TIA 89 has everything. And this does too. You might have to do a little Google search, and I'll try to find, the other thing is, I believe in Canvas, I believe I posted a manual for some of those calculators. Check and see if I posted anything for an 89. Because the 89 is the most common one in this room. Okay, let's take a little break here and unpack this for a minute. Let me try something.
There's a Voyager handbook, and then there's this TI-89.
Is the TI 89 there?
And there's-
Take a look at that and see if you find what you need. Did you find something?
Distribution.
Like, not much of it.
to be in class and you really know what's going on. And people they don't care about that like this. We don't know what it is. Really?
Yeah, and he got the right, he got totally fucking unrelated. It's just like then it's more time.
Oh.
Over next Tuesday.
Oh.
Cause he fucking, this just
And
says
he
that.
also when I came out, I saw one for he finished the
I finished it a little quicker.
really?
Or a couple minutes. But he was so quick, he was quicker. I mean, there was like 3 people before me, and then me.
Yeah, in 2 weeks.
But I couldn't find much of it. I said, oh my God, because I was the only person that watched it. I always when I see
Three exams.
Because they put me.
Because like there's so much material for electronics, it's like
the thing is, one of the important thing is that I shouldn't put this stress on people when I'm doing exam because
Yeah.
I was like, I don't know anything about this. I would be the same with this. I need to make something on the same end of the exam. I don't understand anything. I have to just think a little bit, also
I like how it's like all
and
this,
start
like,
to
more
more
like
like trying to just get back to my job. Just like when I started, I didn't know how to do it. And I said, oh my God, I failed. Because I don't know anything else.
oh yeah.
Slowly I started just like stack up. Yeah.
Got
It
me
just
honestly.
made me really quick.
Like what is why they like that this is the hybrid model?
No, that's the.
Oh yeah, I hope yeah.
Especially.
So the hybrid model doesn't include
Oh yeah. Oh, apologies. Candidates who knows the board will be some, what is it? What is the clock? They just and we're speaking of it.
Did you find it already on your calculator? Do you have to download something?
I remember seeing this.
It's on the stat.
It's under stats.
Yes.
Yeah, stat list.
Okay, good. I mean, I knew it was there. Yeah.
It was chicken coop, right? So he runs around the
was on channel two, just
Really?
randomly ran across it.
Yeah.
I think
Yeah. It'd be like, I think honestly, it's only two wins. Maybe, Idaho State.
We've had some good years though, have we had any good years?
My first year, we did pretty solid. We had like one or two wins in Boston. My first year, I think we were 6-5 or 7-5 or something. Last year, we were like just average, like 5-5 or like 5-6. Just for, and then this year, it was pretty tough. But this year was also like the hardest schedule we've ever had. So like all the people that look at all the schedules and rank them all, they're like, oh, Portland State is the hardest schedule.
Was that right? Because, you played like OSU.
We played Oregon last year.
You played Oregon last year.
Last year, we played Oregon, we got beat 81-7.
Okay, okay.
This year, we played,
Now, the last year, did you lose to a team in Texas by like a score like that, but then the next following week,
No, it was the other
you
way.
beat somebody else?
so we lost to Oregon that 1 week, and then 2 weeks later, we beat a really small school from Texas by like 90 points. We beat them like 90 points.
Yeah, isn't that funny?
Yeah, but this year we lost to Washington State 70-40. Got beat up in that game. And
You
then,
scored 40 points on
I know, it was
State.
actually
Come on.
close. Like, it was neck and neck, and then the third, fourth quarter we beat them.
Yeah.
And we also played Boise State. I don't remember how that game went, but it didn't feel as bad as Washington State.
Is that right?
But
Interesting.
they also didn't have like their best player playing this game. Ashton Genty, the running back.
Didn't play in that game?
He had the ball like 4 times, and in his 4 carries, he like killed us, and then they just pulled him out for like 5-10 minutes. Because they're like, yeah, we'll save it.
All right. Have we had a few minutes there to digest that first hour? Okay, let's see what we can do now. Let's see, I'm a glutton for punishment, so even though I didn't win last time I tried this, I've gone back into MATLAB. I'm in MATLAB.
Okay.
So let me turn this back on. Okay. And so I wanted to, let's see, are we doing it?
No, it's not on.
Really?
That's green, but
It's green. Okay, it's coming. It's like
Maybe
me.
you
It's
have-
like me in the morning.
maybe we have to turn off the light. I don't know.
We're getting there. We're getting there. I can turn off more lights if you'd like. Let's see.
Yeah.
Ooh. Okay, what's going on there? Okay. Anyways, I just wanted to see where we could do it right here. Let's look at what some of these distributions look like, these binomial distributions, and generally like what we did on that second homework assignment, we can be randomly generated. This time, since there's a finite number of values x can take on, then let's just actually compute the actual PDF. And so let's see what we can do. So let's suppose that let's look at the binomial distribution. Which one is it? This one? That's not the right symbol for a comment, is it?
No, it's a percent.
No, it's wrong. Okay, Andy. Yeah, here we go. The shape of binomial distributions. Okay. And so let's start out. And so what were we doing with this last one? With this last one, we had 10 trials and P was 0.3. Okay, so let's see. Let's let N be 10 for the number of trials. Let's let P be equal to 0.3. Okay, just to simulate, to see what this might look like. We saw, let's create a vector for x, and x can take on values 0 through 10, right? Right? Okay? So let's let x be 0, vector 0 to 10, okay? And that's creating a vector of length 11, okay? And let's now compute the probability for each of those, and I'll call it PMF for probability mass function is, and one way to get about it, by the way, there's lots of different avenues to get to this same street in MATLAB, but one is binomial PDF, okay? And by the way, this is kind of cool that for a lot of these distributions, you can go whatever the name of the distribution is. PDF gives you the actual probability value. You can use RND to randomly generate values. You can use CDF to generate cumulatives. Okay? And specifically in input X, when we have n trials and the
P.
probability of a success is P. Okay? And I'll hold that back for a little bit. Let's just see what we think about this. Okay? Right? By the way, what's the mean of, what would you say the mean of this distribution is?
0.3 multiplied.
And n times p, so the mean is 3, right? Right? And so by the way, the mean is the sum across all the x's of x times its weight, right? And so we've got a vector x is, 0, 1 down to 10, right? We've got this other vector probability mass function, right? And what that will have in it is px of 0, px of 1, ... down to px of 10. Do you see how that's coded in there, right? Right? And so if I have these two vectors here and I want to come up with this, does anybody see how using those vectors we can get there? Looks to me like a dot product.
Yeah.
Right? Because wouldn't the dot product be this times this plus this times this, so forth and so on? Isn't that what a dot product is, right? And so absolutely you should be able to go, did I even do it? No? Okay. If we're interested, the mean is the dot product between vectors x and pm. Let's just see what that looks like. Look at that. There's our 3. Okay, so that seemed to work.
PMF.
And what does this graph look like? Okay, and by the way, what are you anticipating it to look like? Now it's discrete, so they're going to be bars. But are you expecting something that looks like this, something that looks like this, or something that looks like that? What are you expecting this distribution to look like? Can you guys see when I do things like that?
Oh, like no. This 3, yeah. Number 3.
See, it's an interesting question, right? Right? And so if P is 0.3, right, then you're probably not going to get as many successes as failures, right? So that means from 0 to 10, you're probably going to get more smaller x values than larger x values. Do you agree with that if the probability of success is 0.3, so leading us to something like this? right?
Yeah.
Right? Whereas that, a fair coin, if P were 1/2, right? You might expect that, right? And so forth and so on. Let me just see, cut right to the chase, right? And how can I do that? I think I can do it with bar. X comma. F. Close that. Let's see what this looks like. Something like that, skewed upward, right? When I say skewed upward, when we say skewed, it's the direction of the elongated tail, okay? Okay? And you can kind of see that even though you might get some 8s and 9s, they aren't happening very often, but you can kind of see where that center of mass right at 3 would be, right? Right? Nice. And if, again, I wonder what, can I, if I change P, do I have to change everything else? If I make P 0.9, right? Let me do my PMF. It's still gonna retain that N of 10, isn't it?
I think.
I think it is too. Well, let's experiment in front of you.
Oh,
What did I do wrong?
position is valid. I indicate
I
must
think
be
it
positive.
sets PMF as like a function.
Oh, yeah, you're so right. Yeah. Equals, yes. Binomial PDF, thank you for that. X comma N comma P. That looks more right, doesn't it?
Yeah.
It's a team effort. I liked that. Let's see what that looks like. Oh, where are you?
Maybe under.
Oh, yes. There you go. How's that feel? Is that what you expected with a P of 0.9? Something like that, right? And what would you expect if P was 1/2? Yeah, and so you get a symmetric thing, okay? Yes. The one other thing that I wanted to see if we could do here, these graphs never really work, but there's something interesting that happens as n increases, okay? As n gets larger and larger and larger, what happens is no matter what P is, it starts to get more and more and more bell-shaped,
Okay.
And so, for instance, and this graph might not work real well, but let's just say, what if I said n was 1,000, right? Not that that's a big number, but, and we've still got a P of 0.9, okay? Now I have to change my X, goes from 0 now to 1,000, okay? And my PMF is, whoops, do it right this time, is the binomial PDF with X and N and P. Okay, I'll suppress that.
Explode.
That looks good. Okay, let's see what I did to us. X and P and F. Close that. We'll take a look at it. We'll see. And you can kind of see there that all that kind of averaging is starting to wean out the two tails, and it's becoming ever more bell-shaped, Okay? okay?
More, it looks more like a spike.
Well, that's only because my scale is so bad. You know, if I started, if we went from 800 to 1,000, it would look a little, it'll look a little broader, you know, yeah, but, yes. Okay, enough there, okay. And so, as you mentioned the spike, let me, get out of here and I'll go back to the document camera, and try to remember that I'm in there. Okay, turn one light back on again. Right. Let's note, since you actually just brought that up, okay, and let x be binomial n times p. Okay, can we do that? Can I do that part of that without it? Yes, of course we can. Okay. We've seen that the mean of x is n times p. Okay. I also at least mentioned to you that the variance of x is n times p times q. Okay. Right. We also noticed a couple things that also see that if y, for instance, is equal to k times x, okay, the mean of x or the mean of y, say that right, the mean of y, the expected value of y is the expected value of kx is k times the expected value of x, or k times the mean of x. Right? We also saw that the variance of y, or the variance of y, is the variance of kx, okay? And when it came to the variance, what happens to that k? Can I distribute through here?
Yeah.
Right?
Yeah.
That turns out you
You
can,
can.
but that k gets squared. K gets squared. Right? That's
We.
k squared times the variance of x, or k squared variance of x. Okay? So with that said, notice where this might want to go. Okay? Don't forget, we have n trials, okay? And each trial is either a success or a failure. Right? Let's define p hat, right, as x divided by n. Right? So what is that p hat? But it's the proportion of successes in your n trials, right? For instance, if we had 10 trials and 6 of them were successes, p hat would be 0.6. So it's the proportion of successes, right? P hat is the proportion of successes. Right? And so, what is this? Okay, what is the expected value of the proportion of successes? Well, that would be the expected value of the number of successes divided by the number of trials, right?
Yeah.
Right? But that's just a constant 1 over n times your random variable x. Right? So that is 1 over n, the expected value of x, which is 1 over n times p, which is p. That is a eureka moment right there. That the sample proportion of successes, the expected value, coincides with the true probability of success.
We just end up with a problem.
Something else happens there, right? And so, by the way, this is a great argument for the validity of taking samples to try to make statements about populations, right? That the sample proportion, the expected value, now don't forget, you run the same 10 trials again, you're not going to get the same number, right? So the expected value in the sample proportion coincides with the true probability, right? Or in other words, in statistics speak, we would say the proportion of success is an unbiased estimate of the true probability of success, right? Similarly, you notice that what's the variance of that p hat, that sample proportion p hat, right? Well, that would be the variance of x over n, right? Which is, by the way, the variance of 1 over n times x, right? But we've seen in the variance that comes out as a square, right? So that's 1 over n squared times the variance of x, which is 1 over n squared times n times p times q, which is pq over n. Right? Here's what's interesting with that, and the other part of the equation. What happens to the variance as n gets large?
Get smaller.
It goes to 0, right? We see that nq over, pq over n goes to 0 as n goes to infinity, right?
Yeah.
Right? You know, this is a little bit comparing apples to oranges, but remember when we were doing that law of large numbers and we tried to do that simulation, we saw that the proportion, the proportion. Oh, in fact, it was the exact same experiment we tried to do in class there, where I've got n down here, and it blipped around, but it ever got smaller, and it stayed consistently blipping around some center line, right? That center line is our estimate for the true probability P. Why does this neck down? Because the variance goes to 0. Okay. Let's bring up another model. Okay. And so
Then x approaches infinity.
and as n approaches infinity, yeah. Okay. Actually, that went reasonably well. Okay. And so, let's talk about another model. Okay, and let's talk about a geometric random variable, the geometric distribution. Geometric distribution. Okay, okay. Now, here, okay, and by the way, if you were looking ahead when you were on your calculator, you might have noticed a couple options below the binomial. There's a geometric there, PDF and CDF there too, so you know what we thought then is true now. So for the geometric, we start with the same premise of a sequence of Bernoulli trials that are independent and identical. Okay, so I'm going to start with that same premise. Okay, we have trials. Trials are independent and identical. Each trial can results in either a success or a failure. Success or a failure. And what's next? Okay. Again, since they're identical and independent, the probability of a success is constant. We'll call it lowercase p. It's a constant. Right? And thus, if it's a constant, the probability of a failure on an individual trial is also a constant. That would have to be its complement, 1 over 1 minus p. Okay, and we can call that q again if we want. Okay, so the layout is kind of the same. The only thing that's different is in the binomial, I specified what n was, right?
Yeah.
Now that n literally becomes the random variable, okay? And so, random variable, I'll call it x. Random variable x counts the number of trials. Until the first success is obtained. Okay. You know, for instance, let's roll a dice until, roll a dice. Roll a dice until it lands on 6. Count the number of trials. Does it happen on the first roll? Does it happen on the 40th roll?
Depends.
Right?
Yeah.
Right? And so, in some ways, this is easier to visualize because there's only really one way it can happen, okay? And so, such a random variable where this is the layout and we're counting the number of trials till we reach a success, okay, has but one parameter, and that parameter is p, okay? Geometric has one parameter, and that is the probability of a success p, okay? And so let's note first that what values x can take on, okay? X could be, by the way, for this random variable, could x be 0?
No.
No, but it could be 1.
Yes.
1 would be the smallest number. In other words, in your
Count.
first trial, you had a success, you stopped. Right?
Yeah.
X could be 2, meaning you had a failure followed by a success, you stopped. Right?
Yeah.
Right? What's interesting about this one is there's no upper bound. Right?
Oh, yeah, it
Right? Because it might be very unlikely, but it could take 1 million rolls to get that first 6.
Yeah.
Right? So x is 1, 2, 3, ...
To the infinity.
Okay? And what's that probability look like? Well, let's just lay out a couple. When x is equal to 1, right, then that means we had a success and we stopped, right?
Yeah.
Right? And what would be the probability of that? Oops, let's put a 1 there. What would be the probability of that you have one, that your first trial results in a success?
Success? Or P?
P.
Yeah.
P. And when x is 2, well, that means the first trial must have been a failure, the second trial was a success, we stopped, right? So px of 2, what do you like for that one?
Fail. P.
Trials are independent.
Oh no.
Trials.
P.
Well, the probability of that success is right there, that's a P, right? But what about that something happened before that?
Q?
Right? So do you believe in PQ?
PQ, yeah.
PQ. And just so we're all on the same page, x could be 3, and that would be the instance where you have 2 failures followed by a success. And px of 3 would be something like, what do you like there?
PQ in power 2?
PQ squared. Yes. PQ squared. And in general, x is some value x, right? That means you have a string of failures and you culminate in a success. And how many failures did you have?
And
X minus 1 of them,
okay.
right? X minus 1. So the probability mass function in a general form looks like P times Q to the X minus 1,
Yeah.
right? Does that seem reasonable? Okay. And
That they call geometric distribution.
it's called the geometric, the whole totality of it is called the geometric distribution.
Okay.
Okay, and by the way, why did we adopt the name, the geometric random variable, geometric distribution? What are we creating here? Geometric sequence,
Okay.
right? Okay, and so, for this geometric, what else do I have there? The probability mass function is px of x is, again, I'll write pq to the x minus 1 for x equals 1, 2, 3, 4, ... and 0 otherwise. Sound good? Does that sound good? Does that sound okay? Okay. And so, yeah, it does. It actually seems like we're creating a geometric sequence there. And without thinking too much about the geometric sequence, it brings us pretty rapidly to the geometric series, right? And so, let me ask us if we remember anything about the geometric series. I added another color here, but I guess I'm going to shout at you in red. Okay, and so recall the geometric series. Calc 3. Okay, and that is the sum as, how do I want to write that? N goes from 0 to infinity of sum a to the n. Okay? Right? 1 plus a squared plus a cubed, ... right? Does that converge?
Yes.
Yeah. Does it always converge?
Yes.
Not if a is 2, because that would be right? Because if a were 2, that would be 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64, and that clearly blows up, right? But I do agree with you that in some context that does converge. Does anybody ever remember where that converges to? What the radius of convergence is on this series? See all the good terms we get to bring up, right? Right? Minus 1 to 1. It converges when A is it converges when absolute A is less than 1, right? Right? And by the way, that's sweet for us because probabilities are numbers between 0 and 1, right? Right? So that's money right there. And in fact, what does it converge to? In fact, the sum n goes from 0 to infinity, a to the n is equal to, I believe it is 1 over 1 minus a. Does that ring a bell to people? Right? Right? For absolute a less than 1, and it diverges otherwise. Diverges otherwise. Okay? And so bringing that up, yeah, I'm going to ask kind of that same question that I started with before. Does this even produce a valid probability distribution? Right? Namely, I think we can all agree that that number is going to be positive. It's going to be non-negative. It should be positive, right? P and Q shouldn't be 0 or 1, otherwise it's kind of trivial, right? Right? So the question is, does that summation add up to 1? Right? Right? And so going back, right? So the question is does the sum as x goes from 1 to infinity, px of x equal 1? Right? It better, otherwise we probably shouldn't be wasting our time in talking about it here, but does it? Right? And so to get it, we can appeal to this geometric series, right? And so what have I got there? We've got the sum, x goes from 1 to infinity of pq to the x minus 1. Okay. Good. First off, let's factor that p to the front, right? And so I can pull a p out here. We doing okay? This looks like kind of the end of class today, doesn't it? Q to the x minus 1. Okay. Now, okay. I notice here that my index needs to be, for this conversion to be accurate to that, my index has to start at 0. I'm starting at 1. But am I really starting at 1? Because if you do this out, isn't that q to the 0 plus q to the 1 plus q to the 2? Can't I just do a change of variables? Right? Can't I let y be equal to x minus 1? Right? Change of variables. Do a change of variable, right? Let y equal x minus 1, right? And so then this becomes p times the sum, right? Well, let me see. Wouldn't y be starting from 0 and going to infinity of q to the y? Yes. So we're not actually removing any of the terms in that summation, but do you agree that that would be p times 1 over 1 minus q? Right? Using the conversion of a geometric, because we have now created a complete geometric series, right? And as long as q is bounded between 1 and minus 1, that's going to converge, right? In fact, we even know what it converges to, 1 over 1 minus q, right?
Yeah.
Well, 1 minus q is frankly just a fancy way to say p, isn't it?
Yeah.
Right?
1 minus q, yeah.
Right? That's
Yeah.
p, the whole thing is 1.
P. Oh, yeah.
Okay?
You just proved
So, wow, believe it or not, we have created, this is a probability a valid probability distribution, okay? Great, and so, I think that's probably it for today, but you'll also remember that when we were talking about geometric series back in Calc 3, wasn't Calc 3 your favorite calculus course? No, okay, that's fair.
It was nice.
It took me forever to wrap my head around why infinite series was even included in the calculus sequence. I've eventually figured